2, 1, let's have fun. Alright, so, as promised, we are now going to learn how to solve homogeneous linear systems of differential equations. Alright, so specifically we're going to focus in on the case where A is a 2 by 2 matrix. We are going to note that for 3 by 3 and higher, all the techniques that we talked about for the 2 by 2 case can basically just be applied with some ins, outs, and some what have yous about how it's going to go, and basically it's exactly like what we saw for second order and higher. So we're going to focus on 2 by 2 in the same way that we focused on second order linear differential equations, and then know that for higher ones you basically just do this, but you just got to keep track of things. Okay. So note, as we discussed, our goal then is to produce a set of linearly independent solutions. Specifically, I need two vectors that do that. Okay. Now, how are we going to do that? So that's our goal, so what's the method? Well, if you remember, we spent a lot of time talking about matrices, and one of the things we talked about were eigenvalues. And there was a very good reason we did that, because let's say you've got a 2 by 2 matrix and you've got an eigenvector and associated eigenvalue. Remember, that means that multiplying the vector by the matrix is the same thing as scaling the vector. It's the whole reason eigenvectors are interesting, right? Because they are affected by matrix multiplication by simply scaling. So it's a nice, appeasing mathematical equation, but as we've discussed, it's had humongous impacts in not only just the world of science, but life itself, right? Google became the horrible company it is today because of that equation right there. And I'm on a list now, but that's fine, I was already on it. Okay, alright, so what happens if you plug that into the homogeneous equation? Specifically note, look what I'm doing, e to the lambda t. Hey, we've seen that before when they're trying to solve differential equations. Now note, I can't just plug that in, of course I need a vector. So I scaled my vector by that. Now note, that's totally allowed. E to the lambda t is a function, so its outputs are scalars, so I'm totally allowed to do that multiplication. Well, when I take that derivative, v is an element of R2, which means it's got, just numbers in it. So its derivative then, a lambda spits out from the chain rule. And I'm allowed to move things around, and thus we see the vector v scaled by e to the lambda t is a solution vector. Nice. All right. So there we go. We now have a method of creating solutions, so now the only obstacle that we need to overcome is, alright, it can create solutions. Does it create two? And if it does create two, are they linearly independent? Alright, and as we saw with the second order linear differential equation situation, the answer sometimes is, yeah, it totally works. But other times, you gotta get a little complex. So let's see. All right, and I already said that, so let's jump right into it. Okay, so there are three situations we gotta handle. The first one is the situation we want to always be in, because it's the beautiful situation where basically life is easy and you don't have to do too much. So let's say we got this homogeneous system. Let me get the eigenvalues for that matrix. So the first thing I want to do is create the characteristic equation, which again is quickly formulated because we know that it's a second order polynomial where the coefficient on lambda is negative the sum of the diagonals, and the constant term is just the derivative of the matrix. Of course, you can just take the derivative of this term right here, the determinant, not the derivative, and work it out, and we get that it's lambda squared minus 1, which means the eigenvalues are plus or minus 1, because again, the eigenvalues are precisely the roots of the characteristic equation. Alright, so if I want to wrap it up, I need an eigenvector for each eigenvalue, and note what I said here, an eigenvector. In order to formulate solutions, I only need one. And with that in mind, that's going to make our lives a lot easier, so we're not going to get hung up on a bunch of stuff. Right? We're going to use these matrix tools, these linear algebra methods, but we don't need the full-out thing. I need one. Right? The method we're about to do tells us how to get all of them, but we only need one. So let's get the eigenvectors for lambda equals 1. They need to satisfy that equation, right? That's what it means to be an eigenvector. We just reshuffled it. And remember, this is where the determinant is 0, which means the matrix is not invertible. So for a 2 by 2, we should see columns or vectors that are identical, right? And here we see the columns or rows that are identical, and here we see the rows are identical. So here we find that there is an equation. Specifically, if we do the matrix multiplication out, we'll get that v1 minus 3v2 is 0. Now, if I want to, I could use this to give me a full-out description of all possible eigenvectors, but for our purpose, I need just one, so I will just pick a value and get it. Specifically, note that I set v2 equal to 1. I didn't pick 0, because that's not going to get you an eigenvector. I picked 1, and that gives me the v1 is 3, and boom, there we go. One eigenvector associated with lambda equals 1 is 3, 1. Nice. Okay. And like I discussed, if you have a computer do this, a lot of programs will normalize. So they'll give you the eigenvalue, and then the associated eigenvector they give you is actually some garbage with square roots. So be on the lookout for that if you are checking your work with systems, with computer systems. All right. So, same deal, if we do that for lambda equals -1, we'll get those. And here we choose v2 equals 1, that means v1 is equal to 1, that gives me n eigenvector. Again, I just need 1, I do not need all of them, I just need 1. Right, so make our lives easy. Alright, nice. So, for the eigenvalue 1, I have the eigenvector 3, 1. For the eigenvalue -1, I have the eigenvector 1, 1. So the method tells me that I can create two solutions by looking at e to the eigenvalue t times the eigenvector. There we have x1 and there we have x2. Now, I have two solutions, 2 by 2 system. I just need to know it's linearly independent. If it's linearly independent, wipe my hands, because I now have a fundamental set of solutions, and thus I would have the general solution. So, are they linearly independent? Smash them together, take their determinant. Hey, it's just 2. That's non-zero. So there we go. The general solution. Every solution to that system is of that form. We got a nice fundamental set of solutions. And we're done. And that's literally it. We did it. It's all over. We've solved the problem. Alright. So, to recap. If you have a homogeneous system, you've got a 2 by 2 matrix, and your matrix has two distinct eigenvalues, specifically real eigenvalues, then pick any eigenvector associated with it, scale them up and add them, and that works. So now remember, as we discussed, there are infinitely many eigenvectors associated with each eigenvalue, but for our purposes, we just need one, because again, we're going to form this general solution by scaling and adding them together. So even though there are infinitely many eigenvectors, well, they're going to get scaled here by C1. So that's already taking into account for the scaling. That's why, like I was saying, once you set it up, just plug a number in and get the eigenvector. You don't need to tell me what all the possible eigenvectors are. I don't care. I just need one to make the solution. Right. The fact that there are infinitely many is taken care of by these scalars at the end. So, yeah. So, once again, constant abuse. Alright, so, this is great for 2 by 2s, and in fact it works for 3 by 3s, 4 by 4s, 5 by 5, 6 by 6. If you have a 12 billion by 12 billion homogeneous system of linear differential equations, and you have 12 billion distinct real eigenvalues, then get your 12 billion eigenvectors and scale them up and add them together. That's it. Alright. That's too easy, so let's make it more interesting. Okay, so the case of repeated real eigenvalues, there are two possibilities. Okay, so let's start off with this, but let's notice something about this. Here, note the matrix is the identity matrix. Note that if I actually wrote it as a linear system, it's a system that's already been decoupled. Right, there is no intermingling of x and y. It's literally, I have got two unknown functions, and their derivatives have nothing to do with each other, just themselves. I could solve this. I don't need to do anything, right? So this tells us that if the matrix method truly does work, it should produce these vectors as the solutions, right? We already know this is what the answer has to look like. So this is actually a good test, because the matrix method should give us this stuff. If it doesn't, then something is wrong. Okay, so let's go in. The characteristic equation in this case is very nice, and we've only got one eigenvalue. The eigenvectors must satisfy that equation. And note that just tells me 0 is equal to 0, so that's just vacuously true. That tells me that v1 and v2 can be whatever I want them to be, which means I can use them to create two eigenvectors, because any choices that you make for v1 and v2 will produce eigenvectors. So note, in other words, everything out of R2 is an eigenvector other than the 0 vector. So I make two choices, specifically two choices to ensure that they are linearly independent. And boom, there we go. The solutions that I knew from the conversion of the matrix system into an actual system of equations, the solutions I expected to get in the matrix method actually got them for me. Excellent. So those are indeed linearly independent, and life is good. So, there's something we need to discuss. Algebraic multiplicity is the number of times an eigenvalue appears as a root. So in other words, the number of times it as a factor is in the characteristic equation. So for example, the one we just saw, the algebraic multiplicity of 1 is 2, because the characteristic equation has 2 lambda minus 1 factors. The geometric multiplicity is the number of linearly independent eigenvectors for an eigenvalue. So, for example, lambda equals 1. That is geometric multiplicity 2, because I was able to create 2 linearly independent eigenvectors for 1. Nice. So in this case, the algebraic and the geometric multiplicity, the algebraic and geometric multiplicity are the same. In general, the geometric multiplicity is less than or equal to the algebraic one. Now, this is a fact that I had repeated to me multiple times in multiple courses when I was a student, and I have never seen, and I never saw a proof of it. The professor for the class always said, yeah, this is obviously true, you can look up the details if you want, and I'm going to continue that tradition and just say, yeah, it's true, you look up the details if you want. Alright, but it is true, the geometric multiplicity never exceeds the algebraic. Well, that then leads us to the following situation. What happens when the geometric is less than the algebraic? So when they're equal, we never have a problem, because it appeared twice as a root, but I was able to create 2 vectors, so I'm happy. That means 2 solutions that are linearly independent. But let's say the algebraic multiplicity was 2 and the geometric multiplicity was 1. Can I still create 2 solutions? So, mild tweaking, a mild reworking of the previous problem. 1, 1, 0, 1. This now is going to have wildly different behavior. Specifically now, the characteristic multiplication is still the same, so there's only one eigenvalue. However, I'm only ever going to be able to create one eigenvector. That 1 up there then locks down v2. This 1 here does not get deleted when we look at the eigenvectors. So that forces v2 to equal 0, which means v1 can be whatever we want, but v2 is always 0. So I'm only ever going to be able to create one eigenvector. So the geometric multiplicity in this case is 1. So we have the bad situation I was just talking about, right? And note, it was not hard to cook something up that had this problem. Whew, so what do we do? Right, so note this situation is very similar to the case of repeated roots for second and higher order linear differential equations. We're going to have to do some sort of reduction of order, right? Because if we're in this situation, algebraic multiplicity 2, geometric multiplicity 1, the method only produces one solution, so we need to find a second one. Now, before, we talked about reduction of order. For systems, there sort of is a reduction of order, but it is nowhere near as nice as it is for the other case. Right, for second order and higher systems, reduction of order, there is this beautiful formula and it works out great. For matrices, it's there. So Remember, for second order linear differential equations, all you would do is take this thing and multiply it by t. That's part of the solution, but there's this other piece that has to be there in order for this method to work. And this other thing satisfies the following equation. So, that p vector right there actually has a name. It's called a generalized eigenvector. So in the case where you don't have enough eigenvectors, there's a way of sort of getting enough eigenvectors by setting up formulas that look like this. Now, we're only going to talk about it for the situation of algebraic multiplicity 2 and geometric multiplicity 1. Other situations, it gets real involved and real complicated, so we're not even going to touch it. We'll just leave it at that. But anyway, that's how you create the second solution. You take your first solution and multiply it by t, so very much like what we did with second order. But now you need to set up this generalized eigenvector equation to get this other part, e to the lambda tp. Okay, so let's actually see this in action so we get a good feeling for it. Okay, so we already know that the only eigenvalue for this is 1, and we know an associated eigenvector is 1, 0. So that gives me an x1, just e to the t 0. Okay. Now, I'm going to create a second solution, and what I need to compute is p, where p satisfies that equation right there. So we set up the same thing we did to get an eigenvector, but now the right-hand side is not 0, the right-hand side is the eigenvector. Now note, this equation tells me that p2 has to be 1, and p1 can be whatever I want. So since p2 has already been locked down as a non-zero constant, let me just choose p1 is equal to 0. Now, it's worth noting here, you can pick p1 to be whatever the hell you want. It's free. You can do whatever you want. But note, I can choose it to be 0 here because that actually wouldn't be a problem. If p2 was equal to 0, then I would need to pick a non-zero thing, otherwise I wouldn't be getting anything interesting. But in this case, we're allowed to get away with it. Alright, so equipped with all that information then, the second solution, which is t times our first solution, plus e to the t times this p vector. We then get t times e to the t in the top, and then the p vector puts e to the t in the bottom. We've got our second solution. Therefore, we're done. So now, note, I didn't explicitly demonstrate it. This second solution is going to be linearly independent when combined with the first one. So this does work. This is a general solution. This does give us a fundamental set of solutions. I didn't show you the details. You can go ahead and do that, but it will work. All right, so to recap everything we just learned, for a homogeneous system with repeated eigenvalues, there are two possibilities. So if the geometric multiplicity is 2, then for each that means that one eigenvalue, I can create two linearly independent solutions, and wash my hands, walk away, I'm done. Now, very rarely does this happen. More than likely, your geometric multiplicity is 1, so the solution you need to formulate is this one, where v is an eigenvector and p is a generalized eigenvector, meaning that it satisfies that equation right there. So you set up the same equation to get the eigenvector, but instead of the right-hand side equaling 0, you put the eigenvector there. All right. Nice. Okay, and like I said, this is very specific to the situation of a 2x2 matrix. For 3x3 and larger, it becomes wild, right? Because note in the 3x3 case, you can have an algebraic multiplicity of 3 and a geometric multiplicity of 1, or a geometric multiplicity of 2, or a geometric multiplicity of 3. You can have an algebraic multiplicity of 2 and an algebraic multiplicity of 1. It gets way, 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 way out there, and so we're just not gonna touch it. But it's worth noting that there are techniques, there are all these things you can do with what are called generalized eigenvectors, but that's going way beyond what we want to do. All right. So we've taken now care of the case of distinct real, repeated real. You knew it was coming. So just as surprising as it was when we were looking at second order equations, even though everything involved is a real number, everything here involves real variables, the method to create the solution is going to require us to go through the complex plane. So if we set this up, the characteristic equation for that matrix is that polynomial right there. Note I already completed the square. Big fan of completing the square. Because I can immediately read off to you the eigenvector, the eigenvalues, they are complex. -2 plus or minus I. Alright, so there are two of them, and they're distinct. They came in a conjugate pair, right? They have to come in a conjugate pair. Now, how are we actually going to find eigenvectors? How's that going to go? So before we go in all guns blazing, let's make a plan of attack. So it turns out that if you've got a complex eigenvector, eigenvalue, then the eigenvector is complex. That shouldn't be too surprising because, right, the complex number needs to scale a vector that needs to coincide with the matrix times the vector. So complex numbers need to be running around, otherwise it's not going to work. Okay, so the associated eigenvector is going to look like A plus IB, where A and B are vectors whose entries are real numbers. So the method tells me that e to the lambda t times v is going to be a solution. But let's see what that's going to explicitly look like by breaking it up into its real and imaginary parts. So in other words, I want to rewrite it so I've got a real thing plus I times another real thing. So Euler's formula comes to the rescue and tells us that e to the lambda t is going to equal to that. And if we multiply the vector by that function, e to the lambda 1t times the vector v1, I did all the work for you, I worked it all out, you get this. Alright, you can verify by doing all of the multiplications out that is indeed what you get. Now note here, this term right there only involves real numbers. This term right here also only involves real numbers. Alright, well I have that, now what do I do? So remember, what we did for second order was we used one of the complex values to get a solution. We used the other one to get another solution. And then we superpositioned our way to real solutions. So that's exactly what we're going to do here. The other complex eigenvalue is alpha minus I beta. Its associated eigenvector has to be the same as the one for alpha plus I beta. The only difference now is that the plus I is a minus I. So it also comes in a conjugate pair. So if we look at the multiplication, you get the same thing, but now with a minus I. So by superposition, I can create a solution by scaling them both by a half and adding them up. And note that that would delete the imaginary term and give me that real part. And then doing the same thing by scaling by complex numbers carefully, that gives me the imaginary part. So these are indeed solutions, and in fact, they're linearly independent. Now, you can go ahead and verify that, but trust me, they're linearly independent. So, we now have a way of producing solutions, linearly independent solutions, from the complex eigenvector we're going to get. We need to pull it apart into its a plus ib terms, then use a and b to solve and just plug in. So look at this formula for x1, look at that formula for x2. Very useful, very helpful. All right, well, let's do it out. So, equip of it, let's actually get it used here. Okay, so we'll reconsider this. We already know what the eigenvalues are. Now note, we only need one eigenvector. We just need to figure out the a and the b for the eigenvalue -2 plus I. I don't need the -2 minus I eigenvalue. I only need the plus one. Okay, now if I plug this in to the formula for finding an eigenvector, I subtract the diagonal by this thing. That gives me this. Now the first thing you might whinge at here is, ooh, wait, those rows and those columns look completely different. They're the same. You may not see it, but they are in terms of scaling. So I claim that if you were to scale this equation by I minus 1, note 1 over it, you would, -1 over it, you would indeed get the second equation. This is because complex multiplication has more information than real multiplication. as we were discussing when we were talking about complex numbers, complex scaling encodes rotations. That's why these equations look like they might be completely different. They aren't. It's just there's a rotation going on that we can't quite see. All right, that being said, that first equation we have that, and again, we only need one, and we only need it in the form a plus bi. So plug in a number. Here I chose v1 equals 2, just so that when I solve for v2, there's the 2 that can cancel. You don't need to choose that, but fractions suck, so let's not encounter too many of them. So now we can pull v apart into its a plus ib terms. I now have a, it's 2, -1. I now have b, it's 0, 1. I have my alpha, it's -2. My beta is 1. So by that formula we just demonstrated, we just plug it all in. So a is that, b is that. So that means x1 is equal to that. So this is something you're going to notice. When it comes to complex eigenvalues, the solutions are less than crisp, let's say. All right. So alpha is -2, so we have e to the alpha t. Beta here is 1, so we just get cosine and sine. And plug in a, plug in b, plug in b, plug in a, and that... Oh, all right, well... I got, that should be a plus sign, not a minus sign. All right, we almost made it. I got the slide 19 before I found something wrong, so that's not too bad. All right, so specifically, all right, that minus there should be a plus. That is not right, so let's fix that first. All right, do a little fix. Okay. That's right, and note, I actually did it correctly over here. Because I knew it had to be a sum, but I didn't write it. That's because I copied and pasted this line and didn't get rid of the minus sign, because I am a hack fraud. Alright, not too bad. Alright, so that means the general solution is this first vector scaled by c plus the second vector scaled by c2. It's a fundamental set of solutions, so we're done. And, oof, I don't know about you, but I'm tired. So let's wrap things up here. Alright, so that means that for a homogeneous system with a 2x2 matrix, if you've got a complex eigenvalues, alpha plus I beta, then the solutions are found by setting up those equations right there, where we focus on the alpha plus I beta, where we don't care about the minus, and we just find the associated eigenvector for that one. So note, if you do the eigenvector for A minus IB, then you got to make sure that you do A minus IB. Do not recommend doing it. Just stick all the positives. Do not introduce unnecessary negatives. We're already going to have a minus signs. Let's not, make life harder than it needs to be. All right. There you go. That's the full story. Now, for larger matrices, you just kind of piecemeal these things together. But like I said, once you get to 3 and higher, it gets the theory gets a lot more muddled than the 2x2 case. So we'll just stick to the 2x2 case. All right, and with that, we're done. So what's left? Well, homogeneous, we know how to solve. Non-homogeneous is next. All right. All right. That's it for today. Hope you liked it.